Assalamualaikum and hi everyone. My name is Muhammad Amir Azamuddin bin Abdul Ghaffar. My metric number is 200238.
And my name is Zakira Amalia binti Muhammad, and my metric number is 2000375. And today we will discuss about on experiment 1, which is the title is synthesis and UV spectra of the vanadium complex. So here, what are we going to present is description of a procedure to synthesize of vanadium complex, explain the process or step to use the UV vis equipment, then explain the use of UV vis spectra on detecting the vanadium complex synthesis on the video. Then calculate the energy and assign the electron transition based on the obtained UV spectrum, which is we refer it on video 1. So as we know that vanadium is special and rare element in the periodic table, it can classify as a transition metal. When the transition element is ionized, they will lose their valence S electron before lose their D electron. Vanadium has 5 electrons that can be lost. One of the characteristics of transition metal is their ability to adapt multiple oxidation states. Then vanadium exhibits 4 common oxidation states, which is plus 5, plus 4, plus 3, and plus 2. And each of these will have different color. The color of oxidation state, and you can refer it into the table, which is V2 plus is violet, V3 plus is green, VO2 plus is blue, VO2 plus which is plus 5 is color yellow color. So let's move on to the procedure of our experiment. First, we must weigh 2.5 grams of vanadium 5 oxide, which is V2O5. Then we need to add 15 ml of water by using the measuring cylinder, and we need to swirl it. After that, we need to add again sulfuric acid, 15 ml of sulfuric acid to that beaker, followed by 15 ml of ethanol. Then we need to put it on steam bath and stir it frequently. It takes about half an hour. Then we need to filter it by using vaginal funnel. We observe that we get orange precipitation on the video in the video. Next, we need to prepare the sodium carbonate while with it 10 grams of sodium carbonate and dilute it with 60 ml of water. Then swirl it. Then we need to transfer the product to the filter and pour the solution into the beaker and wash it with water to get the maximum yield. After that, 3.2 grams of acetyl acetone, which is added to the beaker in the previous step. Next, check the pH of the solution, then add a few drops of sodium carbonate. And when we add the sodium, when we add that, uh, we will see the bubble will form because of the reaction. Keep adding the sodium carbonate until the solution neutral or blue powdery precipitation is appear. Check the pH again using the pH indicator. Solution is complete when pH reaches 7 or above. Filter it again and dry it using vaginal funnel and collect the yield. Rinse the product with ethanol and filter it again. Last step is wait and record the mass of the yield. So this is the overall equation of our experiment, which is our product is VO2. So to get the better result, we must take the precaution step. First, when we measure the solution using the measuring cylinder, volume of the liquid should be read from the base of the meniscus. like in this picture, we need to read it at this level. Next, when we handle the chemical like sulfuric acid and sodium carbonate, we must handle it in the fume hood that can reduce or eliminate exposure to volatile liquid, dust, and mist. Next, when using the Bushnell funnel, using the steering rod to filter solution down, the steering rod at the side at the beaker to avoid the splash, like in this picture. This tip we get from the video. Okay, so I will pass this presentation to Azam.
Okay, so generally, UV with spectroscopy is a measurement of attenuation of a beam light passing through a sample or after reflection from sample surface. So these are the general instrument used to perform UV spectroscopy, which are light source, monochromator. In monochromator, we have prism and gratings, sample solution, cuvette, um, detector, and also recorder. So next page, please, Sakira. Okay, so the component of UV spectroscopy, light as the energy source, monochromator used to break the polychromatic radiation to monochromatic radiation. In monochromator, they have prisms that disperse polychromatic light from the source into its constituent wavelength, and gratings that use in monochromators of spectrophotometers operating ultraviolets, visible and infrared regions. Cuvettes used as a sample holder that have two opposite opaque sides and two opposite transparent sides. Detector used to generate electronic signal which are proportional to the transmitter light, and recorder used to display electric signal in form of graph. All right, so the general principle of UV spectroscopy is absorption spectroscopy based on phenomenon of electronic excitation. When UV pass through sample, atom or molecule will absorb the energy, then move from the ground state to the excitation state. If it occurs, the residual radiation, when it pass through prism, it occurs spectrum with gap in it, which called absorption spectrum. So the light source will pass the polychromatic radiation to monochromator, and monochromator will convert the polychromatic radiation to monochromatic radiation. Okay, then the light will pass through the sample holder containing sample solution to the detector, and recorder will receive the electric signal from the detector and display it in the form of graph. Okay, so this is the picture of instrument, which is UV spectrophotometer that have a chamber and lid used to insert the cuvette inside it, and control panel used to to uh, to get the result. So next. Okay, so here are the steps to use UV spectrophotometer. So for the first run, we need to do a blank solution scan. Okay, so both reference and sample contain just solvent. Okay, so first we need to rinse and fill 2 cuvettes with solvent. Okay, after we rinse the cuvette, we need to wipe the transparent side. Okay, there are two sides of cuvette, which are opaque side and transparent side. We use the opaque side to hold the cuvette, and transparent side we need to wipe it using clean wipe to make sure there's no fingerprint, grease, droplets on the transparent side, because the light in the UV spectrophotometer pass through the will pass through it, and we don't want the light rays will diffracted. Okay, so second, we need to insert the cuvette in the chamber, one in the blank side and one in the sample side. Okay, when we put the cuvette in the chamber, we need to make sure that transparent side are in the east-west direction. Okay, then we close the lid and we move to auto zeroing step. Okay, turn on the machine and wait for it to initialize. Okay, then press button 2 on the control panel to access the spectrum and make sure the data are correctly input. The data, we need to make sure the scan range should assign from 400 to 800 nanometer, and absorbance value need to range from 0.0 ampere to 1.50 ampere. Okay, next, press the auto zero and wait until the spectrophotometer beep a sound. Then take out the sample cuvette. Okay, we need to take out only the sample cuvette and discard the solution. Then we are ready to run the sample solution. Okay, so rinse the sample cuvette that we discard the solution with the sample solution. Okay, rinse the cuvette uh, with sample solution, then fill the cuvette with solution until 4 to 5 high. Next, okay, then after we fill it, we place the sample cuvette back into the sample side in the chamber, then close the lid. Okay, so next we need to press the start button, then notice how the graph form and check the highest peak of the graph, which means that will be the highest absorbance. Okay, so press F1 to zoom. Okay, on the control panel, we need to press the one F1 to zoom, F3 to scale. Okay, then we press F2 for the data processing and press button 3 to see the maximum absorption wavelength and absorbance value. So after that, we need to press F2 to print the spectrum result. Okay, so as we know, UV spectrophotometer can use to detecting vanadium complex, which it can determine the concentration of vanadium. Okay, we can get it by the information from the graph form. We get the information of the highest peak on the graph. Okay, then you calculate it. Okay, to determine the concentration of vanadium complex, we use plastic cuvettes because cuvette have three type of cuvette: plastic, glass, and quartz cuvette. Okay. As a sample solution, we use 0.1 molar vanadium. Sorry, vanadium complex. Okay, then as a solvent, we use 4 molar sulfuric acid. The cuvette were purged with N2 prior to adding the sample and were then sealed with parafilm to exclude air, and the measurement also taken as quickly as possible. Okay.
Okay, next is we need to calculate energy and electronic transition. So this data we get from the video. To calculate energy of photon, we need to use the Planck equation, which is E equal to h c over lambda. So at 598 nanometer, we just insert the value of h and value of c, which is the constant, and divide with value of wavelength, which is we need to convert it into meter. Then we get the answer, which is this. So for the for the C180 nanometer, just follow the same step with the previous, which is insert the value of h and value of c, then divide by the wavelength, but remember to convert it into unit meter. Then we get the value of energy. So when the wavelength is increased, the energy of photon is decreased. We can conclude that they have inverse relationship. So the complex of the VO A cap 2 has an oscillation state complex of plus 4, which the vanadium 4 ion exists as D1 from it reduced from the D5. Using the crystal field theory, there is electronic repulsion between the electrons of the active ligand and the electron on the vanadium metal ion, which cause the initially degenerate 5d orbital of vanadium metal ion to split into two different levels, which is this. So, as we know, vanadium slightly displaced above the plane of the four oxygen atoms that attach to a cat ligand. We know that UV rays will detect from 200 until 800 nanometer only. A d electron can be excited to a higher d orbital by absorbing visible H, visible UV. In this experiment, we noticed that two broad absorbent in the UV data. Visual color change slightly with the coordinating base. Each absorbent related to specific D transition, which is dxy to dxz and dyz. Dxy to dx squared minus y squared. It requires energy to excite electron from dxy to dxz, dyz orbital or to the dx squared minus y squared. From the graph, we notice that lower lambda maximum at 598 nanometer is higher than energy from the 808, 608 nanometer. At at 598 nanometer, we'll notice that electron excitation from the dxy to dx squared minus y squared, which is sigma star. And for the 608 nanometer, electron excite from the dxy to dxz and dyz, which is pi star. Same happen with the uh, when the base increase when the base strength increase. So wavelength at wavelength of higher d orbital increase means that absorbed energy will be increased. If the V if the VO bond increase, it means that Lewis base stress is also increase. Okay, that's all from us.
Okay, so for the conclusion we got from this lab presentation, we know the procedure of synthesis vanadium complex, which we use the vacuum pump instrument and we observe the color change of vanadium complex. We also know the instrumentation of UV spectroscopy when the light pass through from the light source until the recorder shows the graph. UV spectrophotometer also can determine the concentration of vanadium complex. Okay, next, so we also know how to calculate and assign the electron transition, okay, based on the obtained UV spectrum. All right. So I think that's all from us. Thank you.